All right, heck yeah. So what I have here is kind of the numbers for the Titan sub. We have its length, for that carbon hole is 2.4 meters. Everything's going to be in meters, in kilograms. But I do go from 6,000 psi. We do keep that here. So what we got? The take home point is that if you did have a breach in the aft, let's say you have your cylinder, and you basically have another cylinder of water that wants to fill that cylinder. Just consider it like a bullet going through a gun, but the bullet's basically the size of the barrel, and when the bullet goes into the barrel, it just stops. Um, and we want to know how fast it's going before it actually comes to a dead stop up against like a barrel with that's got something covering the end of it. So anyway, density of water is this 998 kilograms per meter cubed. And so if we do you know, here's the area of the inside. So it's basically just the area is a meter squared. And then the length is 2.4 meters long. So heck yeah, you're going to get a mass of the water if you filled the sub would be 2,000 about 2,500 kilograms. Double that for pounds, you know what I mean? Over 5,000 pounds. Okay, so what I do is you can do this for any F equals ma problem. You can figure out the forces, and heck yeah, you got 6,000 psi. We convert that to kilograms. I don't know why I did that, but you convert that to Newton meters squared. And then you figure out, hey, this is the area of the inside in meters squared. So you can find the force. And just to show you where I got those perfectly, hey, let's do that. So anyway, this force is 42 million. 42 million newtons is pushing that slug of water into that sub. Okay. And the time frame just has to be real tiny. I did this a few times, but the take home point is that that water is going to hit the end of that in 0.016 seconds. Okay, because right here. Okay, see, once this gets negative, then we pass. So this is past the point of no. You can't push through that distance. So the whole thing was 2.408 meters, and then so this is too far. So this is the water going all the way up to here. It takes 0.016 seconds, and so we'll highlight that. Now, this video, I'm not going to go into the just all the details of how I did this because we're going to make it in under 10. We're just going to do the take-home point here. Uh, so yeah, so it takes that much. The acceleration is all right. So we said F equals ma, right? So if F equals ma, then A equals well, guess what? F divided by m. All right. So there's our force. You know what I mean? So that this was our initial force divided by the mass of the water. But guess what? We even have a force total because the inside of the sub, well, it's got atmospheric pressure. You know what I mean? It is, and what does that mean? Well, it means that when they capped it at the surface, they have a volume of air inside the sub. Now the even with the pressure, sure, the volume might change just a little bit, but not too much. And it's the same molecules of air in there. Uh, so this is always going to be 15, except when you have a breach and you have all that water pushing into the sub. Now think of like a air bike shock. Basically, you have a piston. In this case, it's a piston of water going into the piston of the shock. At some point, that's going to slow it down, right? Well, and that's what we wanted to know. We wanted to know, well, when is this pressure going to increase that it's going to match the 6,000 psi pushing in? And it's not a pretty story. So if we follow this, because if we go to if this is our length, 2.48. So what's half that? 2.408 divided by 2. That's 1.2. So if we go to x is equal to on this side 1.2, we should see the pressure doubles. Or if we just look at the pressure side, wherever that's 30, Heck yeah. The length is 1.2. Okay, perfect. And then what happens is when you get down here, and we would better just erase half of this stuff. Okay, so here's the force on the inside. This is in PSI. Oh, let's just go to the bottom, use our tools. There we go. All right, so like right here, right when it hits 6,000 PSI, well, it's already at 2.4 meters. Well, didn't we say the whole thing is at 2.408 meters? Yeah, and this hits 6,000 PSI at 2.402. So basically, you have to get down to 6 millimeters. That's what that says right there. 6 millimeters um, before the pressure on the inside can actually do anything to change the acceleration. Because this was the acceleration and this was the velocity. So right at the beginning, that slug of water for an infinitesimal. This is what we're talking. We're talking infinitesimal. The time is 1, 2, 3, 4, 5, 6, 1 millionth of a second. And do I even have that right? I would imagine so. Uh, 1, 2, 3, 4, 5, 6, a millionth of a second. So at a millionth of a second, no water is entering the sub. But then at 2 millionth of a second, whoa, okay, looks like you got some velocity of water coming in. And even a meter a second, when this hits 0.5, that's 1 mile an hour. So there you go, 0.5. So at 31 millionths of a second, you have 1 mile an hour of water coming in the sub. This is if you had a perfect, just Popola breach. Um, but it is good to actually show, it is simplified, but it does show you the physics here. Because the take-home point was like, well, why did if the leak was in the aft, well, then it's just obvious that the window in the front's totally just blown out. And why is that the case? Well, let's go down here. And because this model actually doesn't even show it. But right here, right at 6 millimeters away, that water is going 285 meters per second. So basically like 600 miles an hour. And it still has to stop. And then so the impact of that, uh, I mean, just even using this model of like, okay, you have the speed of the water pushing up against the outside, and it still hasn't even stopped. Just let's pretend like it once it gets there, it just gets to keep on going. That's what my model does. That's why it goes negative. But yeah, the pressure right here is 369,000 psi, and it doesn't take into consideration that this water will actually has to stop. So yeah, it's very easy to get over 1 million psi, on the interior of those surfaces just with that water rushing in, gaining velocity, and then F equals ma means that if you need to change that velocity, and you do, that water is actually going to stop, dead stop, and well, you're going to have a force there, and and then the time it takes for that change in velocity. That'll indicate, well, that's the definition of acceleration. Definition of acceleration is, okay, we went from 284 meters per second to 0 meters per second in how long? I don't know. It looks like a millionth of a second. Or I mean, yeah, just and it's probably not that small, but um, yeah. And then your pressure just is astounding. Um, and that's if it was just concentrated on the like the front part of the sub, if that was still intact, as this slug of water is kind of getting all the way to the end. But anyway, at least it's a model that incorporates two things. One, I could have just done, like I've done this before, where you just incorporate the speed. If you don't incorporate the inside pressure, yeah, this just goes to 288 meters per second, and you got to slow it down at some point. And you ain't like, if the water enters the sub and then halfway there's something to actually slow it down the other halfway, just equally, then you might have structural integrity of the sub. But no, that water's just increasing in velocity until it hits something, and it's going to hit something just right at the last, millimeter. And then once it does hit it, that change in velocity is going to be drastic, and the increase in pressure is tremendous. So over 1,000,000 psi guaranteed. I don't obviously if I turn this to like 1 billionth of a second, yeah, it would be sky's the limit right here for the um uh but yep. But that's ideal. You know what I mean? But anyway, it's close enough to what the pressure would be. What the pressure would be when when the water hits the end of the sub, and why the glass window would be broken out. But anyway, so this is how I like to do basically every F equals ma problem, because F equals ma means you have an acceleration. You have some sort of initial velocity, which is zero. All this acceleration means is, hell yeah, your acceleration is going to change by that many meters per second every second. But this thing takes place in such a fraction of a second, you have to use just even an infinitesimal amount of time, and then multiply 1 millionth by this. Okay, and then you get the change in velocity, which is 0.017. See how I took this times 1 millionth basically, and then you get the change in velocity. But now that we got the change in velocity, we can change our positions different. And because we only have the length of the sub to work with, then that sets the boundary there. And well, what's the other thing? Yeah, and we know the interior pressure of the sub is a function of because like we said, it's a function of this position. That's why. Like if we take a look at this. Oh no. Yeah, this let's see. Nope. It must be this. This force. Yeah, the force interior is equal to the force well, all sorts of things, but it's a ratio of the total length divided by the total length minus what's left of it. So once you get to the halfway point, you double it. Once you get to the quarter, you quadruple it. So this can get exponential as the cylinder. Just like any bike shock, as you bottom it out, the pressure can increase kind of exponentially until you kind of hit a max force that's going to slow you and stop you. All right, but yeah, the whole take home point was that just wasn't much at all. I was actually real shocked that even if you had water come in on one side, the air molecules, they're nothing. That mass of air molecules ain't slowing down that slug of water at all, and it's going to violently impact the interior of the sub, especially the front. It's going to blow out that window. So this video is just, hey, share some math, share some engineering, and share how I do problems, because it's a good way to model things. Now back up here, yeah, this velocity is the initial velocity plus the acceleration times the change in time, because acceleration is just change in velocity divided by the change in time. So, well, isn't just velocity? What if you multiply by acceleration by time? Well, you get the velocity. Change in velocity divided by change in time, multiplied by a little bit of change in time. Well, you get the velocity. Or you get the change in velocity. I should say that. Um, so if this was the original velocity, you're going to get the change in velocity, which is going to be this multiplied by change in time. Very, very small change in time. That's going to be the change in velocity. And the next one's going to be the same. So I'm glad I showed you the change in velocity. And yeah, those are for other videos if you want to know exactly how to set these up. But it's just way easy to set them up in Excel, especially if it's F equals MA. You don't have to integrate. And anything F equals MA, yeah, you don't have to. You can just use integration if it's just 6,000 PSI pushing in, and then no other resistive forces. But it's really cool to set these up, because you can set up like 3 or 4 parameters and have them play out where you don't have to use any integration or complex integration. You can just have Excel do it for you. All right, well, this is my shot at making more math videos, and heck yeah, it's probably under 10 minutes. So anyway, happy to make these, and guess what? That's a video. All right, I think I want to add one more thing here. Like, what's the take-home PSI? Well, I think it could be as high as approximately 5 million PSI, but I'm gonna roughly say, shoot, any interior section of that sub could easily see 1 million PSI. And basic modern materials, even grade 8 steel is only rated to 150,000 PSI. But heck yeah, carbon can take a tensile strength of 500,000 PSI. But definitely, I think we all want to know why that window got blown out. Well, it is because it didn't have a chance. You know what I mean? It's not rated to 1 million PSI. It wasn't even rated to the Titanic depth of 6,000 psi, as we all know. But anyway, so how do we do this? Well, and we could have done this a lot simpler. We didn't even have to use the interior pressure, kind of slowing the equation down, slowing this acceleration. Because even like right here, see, this is our acceleration. It's slowing and actually is going negative. But anyway, without this interior pressure, part of our calculation, just the speed is 288 meters per second. But we're going to use 285. And we're going to say, yeah, at about 6 millimeters to go, this 288 meters per second of water, that weighs 2,500 kilograms, has to come to a stop against the front or that window area of the sub. So what we need to find out is the acceleration. And the first thing we need to figure out is, well, we have a change in velocity. We know that it's got to go from 285 meters per second right here to 0. So that's our change in velocity. Our change in time is, well, the amount of time from here to here. And so that's our change in time. So we're gonna look that up. So yep. So it's just this minus this. That's our change in time. And yep. So what 20 millionth of a second. And so definition of velocity is change in velocity divided by change in time. So this is in acceleration is in meters per second for second. So there's our acceleration. F equals ma. We know the mass of the water that had to slow down after it hit the interior of the sub. Okay, so you get a huge number in newtons. Convert to pounds, you get still a huge number. Divide by the area, the interior area of one of the ends of the sub. And yeah, you get right here, you get 5 million, basically 5 million PSI. So yeah, enough to pop kind of the whole guts of that. Well, especially the window. People are, why is the window missing? Well, any sort of breach, even if it wasn't on even if the breach wasn't on the aft side, even if it wasn't on the back of the sub side, where you have the water rushing towards the front. But that's from the transcripts. It sounds where the breach was. It was towards the aft of the sub, and then you would have water wanting to move from the aft to the front. And it might not be this ideal. It might not be like, yeah, the end of it just pops off and you have water rushing in. But even so, you're still going to generate a whole lot of velocity of water. That velocity, that mass of water inside that cylinder has to come to a stop to change. And it's all F equals ma. To change the velocity of that mass in such a short amount of time, that's where we get kind of that final pressure. But anyway, awesome. So thanks for joining me. And I kind of want to make more of these. And if I can make them under, I know this one's now about 20 minutes, but if I can make them under 10, 20 minutes, heck yeah. All right, that's a video.